talking about limits. And limits and continuity go hand in hand. A continuous function is going to be a function that has no breaks in its shape. So this is a continuous curve. Anybody know what this is the curve of? Sine. Sine of 0 is 0. So this is a continuous function. Sine is a continuous function. So again, a continuous function is a function without any gaps. This example down here is not continuous. This is a discontinuous function because right in here, we have a jump from the top to the bottom. In calculus, it's very important to understand that there are certain functions that must be continuous. A car traveling. A car can't just randomly be in point A and point B. Time travel does not exist. So for the purpose of this class, the distance between a car and its destination will always represent the change in distance as a continuous function. The velocity of an airplane or any object's velocity will be continuous. The time it takes you to read this sentence, and then things that are like not continuous, if you were graphing your age, you're 14, then you're 15. So age would look like what type of function? An integer function. The int, because it would jump from here to there to there. The number of words on this page versus the number of words on the next page, and then the amount of water drank. So there are functions that are discontinuous. So these are examples of functions that are not continuous. You can have discontinuity at a point. You can have discontinuity over a range. You can have a jump. You can have a hole. Here are continuous graphs. So a common misconception that is in a lot of textbooks is that if the limit as x approaches a of f of x equals f of a, but does not take into consideration the domain. So here's a function where x equals 1 is not in the domain. We can fill in that hole with a different point or a point that makes it continuous. So that leads us into today's continuity lesson. So there are three conditions that must occur in order for a function to be continuous. The first condition that must occur is that the function point we care about is in our domain. The first condition that must occur is that the function point we care about is in our domain. The second condition is that the limit must exist. So in order for the limit to exist, the left-hand limit must equal the right-hand limit. So if the limit exists and the point is in our domain, then the function is continuous if it equals the point at that spot. Does that all make sense? So it must be in the domain. The left-hand limit must equal the right-hand limit, and the limit as x approaches a of f of x equals f of a. If a function is not continuous from both sides, if a function is not continuous from both sides, it can be continuous from either the left or the right. If a function is not continuous from both, it can be continuous from the left or the right. So we call that right continuity and left continuity. Look at how or right hand continuity sometimes. A function is continuous from the right if the limit as x approaches a from the right of f of x equals f of x. So it is continuous from the right. The limit as x approaches a of f of x equals f of a. And it would be continuous from the left if the limit of x approaches a from the left of f of x equals f of a. We also talked about continuity on an interval. So in your homework tonight, we're going to put intervals of continuity. So a function is continuous on an interval if it is continuous at every point of the interval. So for example, 1 over x has continuity on an interval if you take x equals 0 out of its domain. Is there glares when you guys sit now? So there's no glare anymore? There used to be like, all the glare. Because I feel like I see a glare, but I'm standing. Oh. Okay. Here are 4 examples of discontinuity. So in these examples, we have a function continuous from different points and in different areas. The first example here is an example of removable. If you were to factor the numerator and factor the denominator, this is where a piece cancels. So in this example here, if you factor x squared minus x minus 2, it factors as x minus 2, x plus 1. So you get x minus 2 canceling. So again, that's called removable discontinuity, and it creates a hole on your graph. So when you cancel a factor, this is a removable hole at x equals 2, and you can see that on your graph. In the second example, that's infinite discontinuity. So infinite discontinuity is going to come if you have a vertical asymptote. So vertical asymptotes create infinite discontinuity. So again, if you have a denominator that equals 0, that's going to give you your infinite discontinuity. So in this case, there is a point at 1 on 0, but it's still discontinuous because the graph was going to infinity around it. So the left-hand limit and the right-hand limit existed, the point existed, but the left-hand limit and the point, or the limit and the point, did not exist. Same here, this is jump. So you have your piecewise, you have the removable. They filled in x equals 2, but they filled it in at 1 instead of where the hole was. And then jump discontinuity. It's like your stepping stones or your staircase. It's going to jump at the end. And an integer function is an excellent example of jump discontinuity. Yeah.
So the last two of both jump discontinuity.
Yes. So the removable and jump are very, very similar, but the hole that has a point filled in becomes jump, because you basically go, oop, jump, they jump down, and then jump back up. Oh. Oh.
Yeah, she's still like 6 months on it.
Well, these guys are important in calcs, so at least they have a good thing.
Oh, no, we're just talking about discontinuity.
Oh, well. At which values of x is it discontinuous, and what type of discontinuity is it? So we're just going to go left to right and figure it out. Yeah. No, it just looks crazy. Okay, following along. Perfect. And what's the x value? Okay, in this example here, we have the greatest integer function. And it says find the points of discontinuity of the greatest integer function. And then we want to discuss, does this have points in which it's continuous from the left or continuous from the right? Okay. So the greatest integer function is discontinuous at every integer because of jump. So x equals integer would be your, points of discontinuity. In terms of a sentence, I would say the int function will have jump discontinuity. At every integer. And then if we investigate 1 or 2 integers, if you look at the limit as x approaches 3 from the left, the limit as x approaches 3 from the right, and f of 3, the limit as x approaches 3 from the left will be equal to what? The limit as x approaches 3 from the right. And what is f of 3? The limit is the any.
That was 2.
Because it's close that thing.
Oh, okay.
So, is this function left-hand continuous or right-hand continuous? It's right-hand continuous because the limit as x approaches 3 from the right equals f of 3. So this is what we call right-hand continuous. And it's actually a right-hand continuous at every integer. And you can still say, though, what you said, the limit does not exist. The limit does not exist because the left-hand limit is already equal to the right-hand limit. So the limit as x approaches 3 of f of x is the end. Here is the function 1 minus the square root of 1 minus x squared is continuous on the closed interval -1 to 1. So what type of function is this? It's a square root. The graph will be what shape? Okay, kind of like a parabola. What does the negative in front of the square root do? So it's reflected. So instead of being a parabola open, it'll be open. Yes. However, it's also shifted and reflected again because the x is negative inside the square root also. It's going to be a little cup. A little bit of a whole bowl. Because this is a circle of radius 1. It's radius squared minus x squared equals y squared. So it's the bottom of the semicircle after you do your flippings and rotations. So it's the reflected, shifted up 1, and it's the bottom half of a circle. So here's -1, here's 1. Plug in your numbers too. So if you kind of want to know what it looks like, plug it in. Plug in -1. -1 squared is 1 minus 1 is, square root of 0 is, 1 minus 0 would then be, if -1 squared is 1, +1 squared is also, so it means it's also at 1. Plug in 0, 1 minus 0 squared is, square root of 1 is, 1 minus 1 is, so I go to the hole. So, is it continuous from -1 to 1? You believe that all of those points exist. Is it continuous beyond -1 and 1? Should I plug in 2? No. What happens if I plug in 2? We get a negative under that square root, which we know is non-real, it's imaginary. Is this function left or right-hand continuous? Yes to which? It's both, right? Because the left-hand limit is going to equal the endpoint and the right-hand limit is going to equal the endpoint. So f of -1 is equal to 1. F of 1 is equal to 1. So to show that it's left and right-hand continuous, what else do I need? I need to show that the limits are equal to 1. So I need to look at the limit as x approaches -1 from the right Because there is no limit as it approaches it from the left because there's no function to evaluate. So the left-hand limit, if it asks you for the limit as x approaches -1 from the left, this is the case of undefined. There's no function to the left because it does not exist. However, the limit as x approaches -1 from the right is 1. Well, I graded like 1 page of them. How does the calculator page? Again, it was not great.
So much worse than the dog doctor. You guys are worse. I listen. No, it's never easy. It's never easy.
Correct. Which one? The one mistake we did make? Maybe, I don't know. I was talking about domain. What's the domain of that? Yes, but why? How do we get that? How do we know that? Maybe not on this test, but just in general. Like, I might even have gone back to chapter 0 test. But it was something that I remember. Yeah, what do you have to do with the square root? Yes. And now we have a quadratic with a square root. So remember how we did these? So then you solve for your points. So this is really like a difference of squares. And then we discover
If the bottom equals 0, top right there.
yeah, but if it's in the bottom, yeah, I can't do 0 under the bottom.
Yeah.
It was the chapter 0, but we never really talked about it because I came to the back and then you guys kind of left. But I did remember that I wanted to reflect on this because you had that square root problem with the domain, and you guys forgot to consider that in part of the domain. No, I never like had it started in my brain to talk about that. What other limits do I need to show that it's continuous on the other side? Exactly. And then I will find a positive 1 from the right and positive 1 from the left. I'm not getting it. This one makes me so angry. How can this be so expensive? So this is left-hand continuous at x equals 1 and right-hand continuous at x equals -1. Let's graph the piecewise. You're saying that, I don't know how I'm going to graph this. Because every time I try to draw a point, it just erases. So I'm going to try it.
This is straight
downward, so you have an arrow to the left. The middle function, we have 1 over x. So 1 over 1 is 1. That's an open circle at 1. And then you go to 3. So 1 over 3 is 1/3. And technically there's a point in there at 1/2. Square root of x minus 3. So again, thinking about the domain of that, x minus 3 would be greater than or equal to 0. Therefore, x has to be greater than or equal to 3, which is our starting point, which is the domain of that function. So at 3, you get 0. And then at 1, at 4, thank you, you get 1. Exactly. I don't know what happened with that. Just like, no, and then it like put weird purple dots on this screen. Look, they're just never going to go away now. No, okay. 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 Find the numbers at which f is discontinuous. Where is it discontinuous? Okay, so my points of concern are x equals 1, x equals 3. At which of these numbers is it continuous from the right, the left, or neither? So is it at 1? Are we continuous from the left or continuous from the right? Where's the closed circle at 1? The left. So at x equals 1, this is left and continuous. And that's because the limit as x approaches 1 from the left of f of x is going to equal f of 1, which equals 2. Yeah. If it says like justify, then you have to put into mathematical reasoning why. Like this doesn't say justify, but like if a problem says justify, then you have to show it. A graph on the AP exam does not count as a justification. Nor does a number one. Unless we words. And then x equals 3. That's right-hand continuous because the limit as x approaches 3 from the right of f of x equals f of 3, which equals 0. Another one more. Yeah, sure. Yeah. F of x. I'm so sorry. I do not know why it does not break out. I think it's PowerPoint, to be honest. Like, I'm going to teach tomorrow, Monday, whatever, back in Promethean to see if Promethean's nicer. Or what I'm going to have to do is literally continue to Zoom with myself and write on like the iPad. I like to stand in front of you. And then it's very difficult. Like if I want to stand in front of you and do that, I'm almost gonna have to like turn myself to desk. It's very difficult to do when I've had it in front. That's why I sit back there. So you're right. You really are my trust in class. It was like with my podium.
Yeah.
The problem is it's so tall, it blocks the screen now. I know. And sometimes this pulls down, but I am really desperately scared to pull it down. It comes down. I know, but I get nervous. I get nervous every time. You're not supposed to.
That's stupid. What are the kind of handles?
Oh no.
If you can only use it one way. I think if you just pull it out, it'll come down. Yeah. Sorry, I was mad. Now it's really close. It didn't have to come down, it came out. But wow. How low can you go? Oh, what? I think that's where we stopped. Oh, it's not. Oh. And I think that's where we stopped.
Could you imagine if I top with it down here? Like what? Like
What's the purpose? This is for the kindergarten.
yeah, but like if they were gonna do it, why not put it up higher and then pull me down? Like
Yeah. Do you think this facility
yeah,
can reach
I
that?
can sit on my ground with a teacher class next to me.
Yeah, it's like.
Oh my gosh. Like you know when I have it up, it's like wobbly.
Yeah.
It's not wobbly. I'm not sitting on the floor just eating.
I did our school. What has it done that?
Like, why can't the right like uh-oh. Yeah, I'll look it back out.
I don't like the sounds. That was just it fixing itself from the first crack.
No, it's like the handles. Oh, it's like a case.
Oh.
That's not actually part of the screen. It's a case on it. I wonder if that's why it's so glitchy.
Yeah.
I wonder if the case is pressing on it.
Right. I would say take this off. Yeah. I don't want to touch this thing though. That's why I don't want to touch it. There we go. And now it's wobbling.
That's what I said. I wish I could just like stabilize it. Like,
It's a back. It's a back.
it's on an axle on the back, and I wish I could just tighten it, but you can't. There's nothing to tighten. I watch it every day. Get like it's a wood, so it can't move left to right. How could we determine the discontinuities without graphing?
Well, I got negative 2.
Perfect. So first factor, what are you looking at? So what does the numerator factor as?
Oh, you just got more stuff.
That's what I was going to ask. I'm like, oh, we're really a spelling.
Yeah, we're CHS students.
I spell everything I have. My mom
Let's
doesn't
do
like
it.
it.
Go with your mom. Isabella Robots here today. She got sent home yesterday. Maybe she got a test. You can't test for like 3 days.
Yeah.
No one tests until
No, because Ella, no, because if it's different if you're vaccinated, they said because Ella now got tested already because she's vaccinated and hers is negative.
And now she's on.
Yeah. Yes, she is.
Are
Ella
you
is
kidding
the
me?
most strict person on the planet in the whole district.
She's definitely not Isabella.
Oh, it's Isabella's vaccinated.
What?
Right.
Sorry, bring it back to the calculus. No, do not ever say that sentence ever again.
Yes, always.
That's a terrible sentence.
What does that simplify to?
So what does that make exactly? That makes x plus 2, or I mean, yeah, x plus 2, which becomes x equals negative 2. Removable. So that means the limit as x approaches negative 2 of f of x is equal to the limit as x approaches negative 2 of x minus 4, which is negative 6. Yeah. Are we okay with that statement? Not the other statement. But I have no statement, so I'm more frustrated. Because we want to find a function g that agrees with f from x equals 2 and can make it continuous. So we needed to find a function that at x equals negative 2 will make the limit match the function value. This is where my removable pool is at. That's what I need to fill. So if I were to graph this original f of x, it would look like the linear function x minus 4, and at negative 2, there's a hole. The limit at negative 2 is negative 6, because the limit from the left and the limit from the right are equal to negative 6. Okay, we want to create a function that will fill that hole. So we are creating a g of x piecewise function such that f of x is equal to all x except negative 2. And we need to find a function for x equals negative 2 that equals negative 6 at negative 2. Exactly. So the function that we need is x minus 4 at x equals negative 2. Yes. Theoretically, yes. Which I have run down as like an optional alternative. But you needed to do the math to find the hole. Yeah. So is it just a typo in the directions where it's saying like to find the x equals 2 to positive 2? Yeah, it should say negative 2. Sorry. In all fairness, on here I wanted it out for a day. So I think I just missed my negative. That was me typing. I think that's really fine. I'm gonna go fix that now. And sometimes like I copy and paste from like my PowerPoints to my note guides. And back in the day, PowerPoint used to not have the equation thing. So I had to like